Alright, so I am doing notes today on relations and functions. Now, first of all, a relation is a set of ordered pairs. Now, the way this is expressed can be any number of ways. You can show ordered pairs in a table. You can show them in mappings, which mappings are when you have something like this and you have numbers. And then X's are your inputs, Y is your output, and it'll show you what, if any, numbers go to which ones. You can also express relations on a graph. So, a linear graph like this, that's an example of a relation. You can also express it in an equation like y equals x. Now, when you are looking at a relation, there's certain things that you can tell about it, like its domain and its range. Now, there is a little mnemonic device called Dixie and Roy D to help you remember what your domain and range go with. So your X values, for instance, are represented with Dixie. It represents your domain. It is the input of your relation, and is your independent variable. Roy D represents your Y variables. So we have range, the output, and it's your dependent variable. So domains are your X's, ranges are your Y's, and that's what we're going to focus on here. So, for instance, let's just say I had a table of X and Y values. So X can be 1, 2, 4, and 9. The Y's might be 0, -1, -3, and -6. When it is disconnected points like this, your domain and range will be individual points. For instance, my domain for this set of ordered pairs would be the set containing 1, 2, 4, and 9, because those are the X values in this table. My range would be the set containing 0, -1, -3, and -6. So let's say I had a mapping. Okay. And remember, mapping is showing your input and output. So 2, 8, and 4, and we'll do -4 and 0 over here. And the mapping's like this. Both the 2 and the 8 go with -4, and the 4 goes with the 0. The domain on this one would be the X values, the set containing 2, 8, and 4. For the range, it's only two numbers, -4 and 0. Now, if we had a graph, the domain and range are not going to be disconnected points. It's going to be a range of numbers. So let me erase this and I'll show you what I mean. Let's say, turn this to where it's X and Y axis correctly positioned. There we go. Let's say I had a graph of a sine curve like this. And it's going to go on forever like that. Okay. This is not disconnected points. There's an infinite number of numbers on this graph. Even between 0 and 1, there's an infinite number of x values because there's 0.5, 0.55, 0.555, and so on and so forth. There's a lot of numbers there, so you can't just do disconnected points. What you have to do is when you go and look at your domain and your range, you have to look to see on your domain, is there a limit to how far left it goes or a limit to how far right it goes? If there are arrows, like on this graph, then there is no limit. And my domain is all real numbers. Now the range is how high and how low it goes. Now in this particular graph, this is a sine curve. A sine curve will continue to go up to here and then down to here. It'll continue on curving. So the range does not go below here or above here. So my range can be written like this. -3 is less than or equal to y, because all our y's are above -3. So -3 is less than or equal to our y values. But you also have this upper limit. So our y values are less than or equal to +3, because it's not going to go above the +3. Okay, let's do a different one. So let's say I had a parabola. Not a very good parabola, but there we go. If I had a parabola, my domain is going to be all real numbers again, because it keeps on going to the right forever, keeps on going to the left forever. There's no horizontal limit. But my range, well, it doesn't go below the origin. So all my y values are greater than or equal to 0. So one more example. Let's look at this. Okay, on this problem, when I go to find the domain and the range, domain are my x's, on my x-axis, it goes off forever to the right because the arrow. But on the left side, my x values don't go past this value here. So my x values are all greater than or equal to this number, which is 1, 2, 3, 4, 5, 6, -7. For my range, well, the graph doesn't go below here. And on the y-axis, that's 0. So all my y values are greater than or equal to 0. So we've talked about relations and how to find domain and range of different relations, done a few examples. But some types of relations are actually functions. Now a function is any relation where the x's don't repeat. So in a function, x values don't repeat. So let's say I had a set of points. We'll do another table. Okay. Okay, I can have 1, 0, 2, 3. This table is not a function because our x values repeat. But this table is a function. Your y values can repeat, it's your x's that cannot. So if you're just looking at individual points, like on a table or just a mapping or something like that, do your x values get used more than once? If they don't get used more than once, it is a function. Now, if you're looking at a graph, what you need to do is look to see if it passes something called a vertical line test. Now, a vertical line test basically is if you have a graph and if you were to draw a vertical line at any point on the graph, would it hit more than once? If it only hits the graph at one point, it is a function. But if it hits more than once, like on this one, if I draw a vertical line, it hits at 2 places. This is not a function because it fails the vertical line test. Now, when you express a function as an equation, for example, y equals 2x plus 7, this is a linear graph, and linear graphs are always functions. You can express functions as f of x equals. Now, you might be asking yourself, well, what's the difference? Why do we have to bother with f of x? That's how you say this. When I can just use y. Well, the difference is, if I wanted to find a specific y value, a specific output for a specific x, it's very easy to do by writing it like this. What this means is I want to evaluate the function for when the x value is -3. And the way you do that is just plug it in. So what I'm going to do is I'm going to take my function and plug in -3 for x. So 2 times -3 plus 7. This gives me 1, which means f of -3 is 1. Okay. So let's say I had 2 functions. Actually, you know what? Let's just keep the same function, 2x plus 7. Let's say I had something written like f of 1 minus f of -3. Well, let's change it. We already have -3. We'll do it over. -5. If I had something like this, what I would have to do is I would have to plug in 1 first. So 2 times 1 plus 7, okay, that's 2 plus 7 gives me 9. Then I would plug in a -5 into the function. So 2 times -5, which is -10, plus 7 gives me -3. Then I take these 2 values and plug them in here. I know f of 1 is 9 minus f of -5 is -3. It's Subtracting a negative is really just addition, so 9 plus 3 gives me 12. So function notation is just a way to say, okay, I'm plugging this in for x. But what if I said f of x equals, equals 11? This means I'm setting the equation equal to that because the f of x, the output, is 11. So I would have to do 11 equals 2x plus 7 and then solve for x. Subtract 7, you get 4 equals 2x. Then you divide by 2, and this tells us the x value is positive 2. So be careful about whether you're substituting the x, the input, or whether you're substituting the output, which is f of x. Now, sometimes, we're going to get to this a little bit more at a later date, but sometimes you might have to plug one equation into another. We're going to start with just expressions. So I'm going to keep my f of x equals 2x plus 7. I'm going to keep that. But what if I wanted to find f of, well, let's not use y. F of b minus 3. It's the same process. I would replace the x with the b minus 3. B minus 3 instead of the x plus 7. I would have to distribute, which gives me 2b minus 6 plus 7. Then combine my like terms to get 2b plus 1. I can't simplify it any further than that because I don't have any more like terms. And later we're going to do something called composition of functions, where we actually do combine functions like this. Alright, so let's take another example. Let's say we have g of x equals negative x squared plus x. Okay. And I want to find, actually let's change it to plus 1, make it a little bit easier on us. If I wanted to find g of x, where x is 2, actually let's make it negative 2. One thing you need to be careful of is this. You have to put parentheses around what you plug in. The reason is this. Now don't put parentheses, when I do put parentheses around it, let's start there. Negative 2 squared is positive 4. Make it negative, I get negative 4 plus 1, which means I have negative 3. But if I forget, and I go and checking myself in the calculator, and I don't put parentheses around it, what the calculator is going to do, it's going to do 2 squared, which is 4, and then negative and negative, well, double negative makes it positive. They're going to have positive 4 plus 1, which gives us 5, which is wrong. So make sure that when you go to plug in something, you put parentheses around it. Okay, so let's take another example. Let's say a minus 1 is what we're plugging in. What you'd have to do is negative a minus 1 squared plus 1. But you have to simplify it now. Well, how do I simplify it? Well, remember, when you square something, what you're really doing is multiplying by itself, which gives you this. Now, there's two ways you can do it. First method is FOIL. Okay. FOIL means first, outside, inside, last. What you do is you multiply your first terms, which gives me a squared, multiply my outside terms, which is negative a, inside, negative a, and last, positive 1. The other way you can do it is the box method. Let me scoot it over. Box method is this. We have a minus 1, so a and negative 1, and a and negative 1. A times a is a squared. Here we get negative a, and positive 1. It's the same process, but it's a little bit more, it helps a lot of visual learners, to put it this way. But you're doing the same process. So whichever way you end up choosing, you should get the same answer. So let's continue working this problem. What I'm going to do next is combine some like terms. A squared minus 2a plus 1, and then plus 1 here. Now you notice I still have parentheses around this. The reason I have a parentheses around it is because I have that negative out front. Because now I have to distribute the negative to get negative a squared plus 2a minus 1, and then the plus 1 I've just been carrying down. And negative 1 plus 1 is just 0, so there we go. Alright. So that's it for functions today. We'll continue a little bit, we'll continue from here talking about linear functions in the next one.